Good afternoon. Well, one of the hallmarks of this meeting so far has been the juxtaposition of material science with design and engineering. So it's a very great pleasure to introduce Richard Friend from Cambridge. His modus operandi is both ancient and modern. Ancient because he is the Cavendish professor dating from the aristocratic scientist Henry Cavendish in the 17th century. Previous holders of his chair have included Clerk Maxwell, Rayleigh, Rutherford, Thomson and Bragg. And Richard's own career was launched from his own penicillin on the bread moment when he discovered that in the late 80s that conjugated polymers had some of the properties of semiconductors, such as emitting light. And I guess one of the hallmarks of his career is that he has worked in such a cross-disciplinary way between materials, chemistry, and physics. The citation for his laureate of the Millennium Prize in 2010, the Millennium Prize of Technology, cited him for his integral role in the rise of plastic logic. Well, I said he was ancient and modern. The modern bit is that he's thoroughly immersed in the entrepreneurial world. He's been involved in at least 3 companies that I know of, 2 of which are very well known. His LED work at the beginning was commercialized through Cambridge Display Technology, which was eventually bought by Sunimoto. The printed transistor work was commercialized through Plastic Logic, and now he has a new company exploiting the properties of polymers to be solar cells, a company called 819. So we're very much looking forward, Richard, to your talk on organic semiconductor science. Thanks very much.
Thank you, Andrew, for those kind words. I hope I don't come across as ancient. I'll go for the modern bit. So this is, it's a wonderful conference, this, and I feel pleasantly outside my comfort zone. So I was trying to work out what sort of talk to give. In part, it's going to be a talk about all the wonderful things that the gee whiz things we can do with organic or plastic semiconductors. But I also want to try to give you a sort of sense of the underlying scientific development. And it was enormously heartening, as I often find it to be the case, that when listening to the exposition from within a corporate company or a research organization that still does research, to have that sort of vision that the future is not what happens next year, it might be a long time in the future, and that very often we get all the way towards achieving all the performance that in principle we could get. You don't always hear that when academics are picking off one another's research proposals, deciding why they're not useful. It's very easy to start a talk on using carbon as a semiconductor because everyone knows about graphene. This is one of these sort of much used images of graphene. I forget where it first appeared, showing undulations in a single sheet, honeycomb network of carbon atoms. And of course, it is the remarkable, in many ways remarkable that a material that has been around for forever in the form of pencil lead was only relatively recently discovered to have such remarkable electronic properties. But graphene does show astonishingly high mobility for charge carriers. Electrons or holes travel extremely quickly and scatter very infrequently as they move travel in the sheet of graphene. Graphene itself has a small problem that in spite of it not being particularly black when it's down at single sheets, its fundamental color is black. It is a semi-metal. It absorbs all wavelengths of light, and therefore it isn't really a semiconductor. If we want to turn it into something which we would recognize as a semiconductor, the best clue that we've got a semiconductor that we like is that it's colorful. And color, which you see here, of course, nature is full of colorful things. Green colors are on flowers, but green particularly. And nature makes colourful molecules not because they're pretty, but because they're functional. And tuning colour so that there is absorption of sunlight, and therefore what we see is colourful, is obviously a smart move if you want to get photosynthesis to work. So what do we have to do to turn black graphene into something colourful? Well, a particular, it could be a molecule, it's actually a polymer chain that we found to be very important is this thing here. It's called polyparaphenylene vinylene. And if you want to work out what it might look like, I can take this structure. It happens to be a benzene ring with a vinylene unit, a CH unit, and then another benzene ring, another vinylene unit repeated. I can actually map it onto the graphene network like that. And I could, so what it's as though I've taken this graphene honeycomb network and chopped off the carbons to either side to leave a chain, a sort of nano graphene ribbon, if you like. As we've done that, we've turned on a gap between filled molecular orbitals and empty ones. So it's now a semiconductor, and it's this color. It's sort of yellow-green. It's actually very fluorescent. So it's a slightly roundabout way to explain why this material is a semiconductor. But what I've shown you is that the essential feature that makes graphene a great conductor is still present here. And that feature is that all the carbons have got only 3 adjacent bonds. There are 2 bonds to adjacent carbons, but a 3rd bond to a hydrogen for most of the carbons along the chain. And where carbon has only got 3 bonds, the 4th bond left over we sort of represent as double bonds, or we don't bother at all when we draw the structure of graphene. But those electrons are only weakly constrained, and they're not tied to one particular carbon-carbon bond. They delocalize. And because they're spread out, we can then move charge up and down or across sheets or chains of these so-called conjugated carbons. Now, there's a huge amount of chemistry, and I decided that chemistry is one thing not to put into this presentation. But essentially, you can chop and change. You can put nitrogen atoms or sulfur atoms in. You can put oxygens in. You can attach electron withdrawing or electron donating groups onto the side of the conjugated molecule. So you can tune everything. And it turns out that as engineerable semiconductors, organics are fantastic. There's much more we can tune than if we're stuck with the inorganics, where apart from silicon and the 3 5s, there isn't a lot that really works. So these are some little images of different semiconducting polymers. They're more or less all the colors of the rainbow. But what you see is that unlike silicon, which comes in a block, a crystalline block, which is sliced into a wafer, and then wonderful things are done to a wafer of silicon, but it's all a high temperature, usually high vacuum process. Here we have semiconductor dissolved in a common solvent. We've now got semiconductor as paint. So semiconductor as paint, if it turns out to be useful semiconductor, and that was a big if, is fantastic, because we can now use a completely different toolkit to start assembling this stuff into useful devices. And the big advantage is that it's all done at low temperatures. So if you want to go for flexible wearable electronics, on the whole, you would rather be able to use substrates, plastic substrates, which, of course, would disintegrate if they were heated up to silicon process temperatures. So in many ways, the sort of key attributes are that the stuff is sort of printable at room temperature, and it's the low temperature that may be even more important. Well, to wander a little bit into the science, there are very different views of how to describe these molecules or polymers, depending on whether you come from a physics background or a chemistry background. If you're a physicist, you would say, well, graphene is not very different from silicon, and electrons are actually completely free, so that if you absorb a photon, you produce an electron and hole, and they'd wander away from one another, just like silicon. But if you came from the chemistry community who've looked at functional molecules, electronically functional molecules, for an equally long time, you would say, well, the excitation is actually naturally confined. It's quite small, because there are strong electrostatic interactions that keep electrons and holes together. And one would point to quite small molecules. I mean, that little fragment is a similarly fluorescent blue material to the green fluorescence we get from the long chain. And that sort of uncertainty as to how we describe the semiconductor science has kept a happy academic community, or several communities, bickering away contentedly for decades. I mean, a number of groups in different ways, going back 25, 30 years now, appreciated that as soon as we could process these materials, we could have a go at making devices. And in some cases, the devices are amazingly simple. So the structure here, where we've got a glass sheet with a transparent indium tin oxide metal, we then spin-coated a layer of green fluorescent polymer and then evaporated a top blue layer of a low work function metal. And that very simple structure is something which gave a little bit of light. It wasn't very much light. Here is an original device. It's sitting behind a glass window in an evacuated brass tube. It doesn't look very high-tech, and there's a little streak of light which you might just be able to see. That was what we saw in 1989. There were other wonderful things going on in Kodak Qingtang using vacuum sublimation to put molecules that wouldn't solution process down layer by layer, producing some lovely LEDs as well. But again, picking up the theme of this morning, it does take a long time to translate what is in principle a possibility into something that is really a technology. And it has taken a couple of decades for organic LEDs to find their way into the marketplace. One of the seminal ideas, which is part realized, is that if you want to use these organics where one obviously would, which is for large area applications, because we can coat by printing, that it would be nice to print full color. We did a lot of work with Seiko Epson back in the late 90s, adapting their piezoelectric print heads, essentially from their domestic inkjet printers, so that rather than ink being seen as something that is just a color, often black, on a piece of paper, we should think of ink as a delivery vehicle for putting something functional in the right place. So if we think of printing not ink but semiconductors, it's possible to print the blue, green, and red subpixels that are needed to produce a full color display. And a lot of progress has been made getting inkjet printing to work. And of course, OLEDs are very substantially in the market, principally through the work that Samsung have done with active matrix organic LED displays. They're actually not made by printing, they're made by vacuum processing. But that has been very successfully introduced for Samsung smartphones. It turns out that organic LEDs are a more attractive display than a backlit liquid crystal display. There are fewer layers. The light emission angles are naturally what you want. The displays are also very, very fast. And they, in principle, are more power efficient. So they look very attractive. By the time you're up at full 55-inch or more inch TVs, they're still expensive. There are some beautiful examples, often curved LED TVs. There is a very nice Samsung demo which does use the inkjet printed red, green, blue color differentiation. And along the way, much to my surprise, efficiencies have got better and better. They weren't very high to start with. And OLEDs look quite realistic for panel lighting. What you actually want for interior lighting is not a point source as a conventional light bulb, but a diffused or an area that is bright enough to illuminate the room. So if you can ditch the light shade, or the luminaire as it's called in the trade, by producing a panel that illuminates uniformly, that's an advantage. And the efficiencies are good enough to do that. So this is a plot of efficiencies. It's actually due to colleagues in Dresden. And it's this plot of uncorrelated, or not obviously correlated variables, which is some metric of performance vertically versus year horizontally. And of course, most plots, unlike the one we saw this morning, where performance had absolutely plateaued before it suddenly got better unexpectedly, this is a more conventional plot where things look useless and then suddenly get very good. So what happened from the early work on organic LEDs, where efficiencies were up at around tungsten light bulb levels, which is already good enough to be useful in a display, a number of scientific breakthroughs, unexpected breakthroughs, were introduced. One of them I'll come back to, but it is the harnessing of spin triplet excited states so that they become emissive, and the other was sorting out electrodes so that the drive voltages dropped to be essentially comparable to inorganic LEDs. But efficiencies have now gone extraordinarily high. Essentially, the internal efficiency of light generation as a quantum efficiency, photons generated per electron hole pair injected, is around 100% for the best structures. I mean, it's a remarkable trajectory. But behind what appears to be an inevitable upward hockey stick, there is always a lot of science. It is not something that was predicted. In fact, I sometimes think it would be amusing to write a sort of article picking out all those learned colleagues who said that these things would never work, and there were plenty in this field. And along the way, there's a huge amount of engineering sophistication. This, for those who like energy band diagrams and remember their semiconductor technology, this represents a structure with a huge, well, in this case, it's 5 different organic layers that have been arranged with offsets. These top and bottom energies represent valence and conduction band levels, but offsets designed so that electrons and holes are fed from opposite sides of the device and then trap in exactly the right place to generate light in the right place to give the right photonic structure so that light then gets emitted as it should. A huge amount of very successful engineering has gone into these very high efficiencies. Well, the LEDs certainly carried the field along, but it's the case that organics do just about everything that inorganics do, and there's been a lot of work on transistors. So here is not a very useful transistor, but a different transistor. It's a transistor that emits light. So what we've got is a structure with a substrate, a couple of gold strips, they are gold, that act as source and drain, and then the grey layer here is a layer of semiconductor. It happens to be this polymer here. And then the light grey layer is a layer of insulator. For this was polymethyl methacrylate, this example. And then there's a layer of gold on top. I mean, it's very thin gold, so the gold we won't worry about that. And that gold gate, what we do is put a potential on that induces charges between the insulator and the semiconductor, and those charges then carry current between the source and the drain. In principle, it's just like a standard silicon MOSFET, except upside down. But what happens with this structure is that we can coax, if we get the biases right, we can coax electrons at one side and holes at the other side, and we've got a voltage of an electric field between the source and drain that pulls the electrons and holes together, and where they meet in the middle, they emit light. So if we move to the panel on the right, you can just make out that alternate sort of dark and not quite so dark stripes. They're interleaved source and drain electrodes. The separation between them is huge in transistor terms. It's 20 microns. It's about the thickness of a hair. This is actually a transistor you can see. So when we drive it, what we're going to do is actually swing the gate voltage around, so we move where electrons and holes meet one another from one electrode across the channel to the other. And here it goes. The light comes out of one electrode a little bit spottily. Not absolutely sure why. It might be slightly some crystallization. And then those who like Maxwell's equations can look at the fringe electric fields around the edge of the device just there. And there is light. Unfortunately, the video fizzles out as the light disappears under the other electrode. Now, we haven't found a use for it apart from it being a nice video, but it's a lovely video. So that is a small segue into transistors. Now, one of the things that one has to do with a transistor is to make a rather more complex structure that requires lateral patterning. I have to say that conventional lithography does a remarkably good job, and of course it's had a few decades to become surprisingly cheap. But one can dream, and I did put lessons from nature in the title of this talk rather rashly, but let me have a go. So one of the things the key metric for a transistor is the distance between source and drain, which has now dived down to about 14 nanometers in the current Intel technology. And of course that's done by brute force with conventional lithography, with an astonishingly sophisticated control of the optical imaging of the photoresists, and it's a very expensive process. Nature manages to make similarly small structures using self-organizing forces, hydrophobic versus hydrophilic differentiation is what will, for example, control the structure of a cell wall with a sort of fatty tails in the cell and the hydrophilic bits sticking out either side of the cell wall. So let's see if we can do that, do some patterning. This is grandly called self-aligned printing. So what we've actually done here is to print a first strip of conductor. It happens to be a doped conducting polymer with the acronym P.PSS, which creeps up quite frequently. It's water-based, so there is a blue drop, because it is blue. And of course it's water-loving, so if we printed another drop on top, it would just fuse and we get a line as we've got here. But if we do something to its surface and make it red, well, different, so we make it hydrophobic, then the next drop won't stick to it. So hydrophobic can be as brutal as putting it in a carbon tetrafluoride plasma, or you can do more sophisticated things by adding some surfactant. So if that works, the next drop won't quite touch. And the question is, how close do they get? And the answer is it's controlled by those same forces that are there in nature. In the Cambridge experiments, we think the number was around 50 nanometers, but that didn't require more than a printer. So I'll just run on to the little video at the bottom, which shows a second line of droplets being printed on top of the first, and the first had got this hydrophobic coating. And amazingly, those structures don't short. They're quite a reliable way of making a thin channel. I'm not saying that is tomorrow's technology, but it's more a sort of concept of being able to access a much larger toolbox of methods for manufacturing. So here is another figure of merit versus year plot, but now for transistors. And it is the case that when we started, our first transistors were, I think that's these plots here, our Cambridge work on transistors. The figure of merit, which is mobility, how fast electrons travel in an electric field, was pretty awful. In the standard units of centimeters squared per volt second, we're down at 10 to the minus 5. The number you have to beat is 10 to the 0, or 1, which is about what amorphous silicon gives in the TFT arrays in the crystal displays. And again, there was a huge literature explaining why that would never be possible, because in order to get to that figure of 1, electrons or holes would have to be able to move without being scattered, not within one molecule or one polymer chain, but over several, traveling sort of coherently over real distances. And lo and behold, the numbers are now actually comfortably above 10. And that's, again, through what appears to be an inevitable process, but behind it always was some real discovery about control of molecular structures and avoidance of the wrong sorts of disorder. So transistors are now pretty good. They definitely provide very effective performance for active matrix drive, being able to set the voltage right at each pixel on a display. So amongst the various either demonstrated or mocked up images of flexible displays, quite a number of those depend on thin film transistors which will be deposited under very mild conditions. This is not depositing silicon onto glass so that we can put them onto flexible substrates. There's a sort of roadmap. I won't dwell too long on this, but the great convergence will be able to have organic light-emitting diodes driven by organic transistors. Actually, driving organic LEDs is quite tough because you have to put real current through them, whereas driving an LCD is easier because you just have to set the voltage right. So that is happening, but not yet. So I think, is that going to... Right, I'll just leave that. So flexibility, it is possible with these organics to get remarkably small bending radii down to a millimeter or less. This is a torture instrument at one of the Cambridge companies, taking a sort of laminated e-paper display and bending it backwards and forwards, apparently without harm. There's a little image here, a beautiful paper from the Samea group in Tokyo, an image from a paper in Nature a little while ago, showing rolled up just a few micron thick foil with active circuitry made on it. So the possibility of flexibility is certainly there. It hasn't yet proved to be enormously important. I'm sure it will be so. So when I give presentations to students who are thinking about what sort of future we'll leave behind when we've gone and they've still got to pick up the pieces, this doesn't sell very well, but it usually gets a few laughs. And at that point, I move on to solar. I mean, partly because I actually think we've got to make solar work, and also because if you talk to people, you know, under the age of 20, they actually really worry about it. So to switch way off what I'm sure is of immediate consequence to Microsoft, solar is really important. This is a slide from Nate Lewis from Caltech from a while ago, which is sort of available on the web, showing obviously a map of the USA and a little red square with 3 TW written on it. 3 terawatts is the average energy consumption, total energy consumption in the USA. And the red box is the amount of land that you would need to give over to 10% efficient silicon solar cells to produce 3 terawatts. Now, if you shove it a little bit right, then you could sort of wipe out Kansas. And the other 49 states would be very, very happy indeed. But it's a remarkably small land area, and it does make very vividly the point that there's masses of energy around, renewable energy around, and it's solar. It's not wind and it's not tide. It's solar. So solar matters. And solar has been doing quite well recently. In fact, you could say that crystalline silicon or polycrystalline silicon has done so well that we don't need to do anything else. So these things here, which remarkably crop up in less sunny parts of the world when there are large feed-in tariffs, like Germany and even the UK, are put up because they're not that expensive. So again, some metric for performance versus year. This time it's cost in dollars per peak watt installed, or peak watt of a solar cell. And that has fallen from several dollars in 1990 to around $0.50 today. The point at which solar was said to be break even in sunnier parts of the world with fossil fuels was $1 per peak watt, and it's gone below it. So it looks as though silicon is really okay for large-scale rollout, and that appears to be happening. I mean, there are serious indications that in oil-rich parts of the world, it's cheaper to generate electricity with solar cells rather than blowing off very valuable oil that should be used for transport to run power generating stations. So the real figure of merit that we should probably go for with solar is not so much the dollars per peak watt, but the payback time. How long does it take for a solar cell or solar panel sitting on a roof generating electricity, which is all used, to have generated the energy which was used to make the solar cell and have it installed in the first place. And of course, silicon is a very energy-intensive business. It's expensive to make. There's energy used all the way through high temperatures, complex chemical purifications. Nevertheless, it's got better, but broad brush, we're looking about a year as a payback time, which you could say is quite good, and as an investment proposition, a year is we would probably be happy with. But nature could never have got by on a year. If you look at some rapidly growing crop, and we're being North American, here is some corn. Corn is the most efficient converter of sunlight into carbohydrate. It has an efficiency of 2 or 3% when it's growing flat out. But if you ask how long did a green leaf here take to be net energy or carbohydrate positive, it certainly wasn't a year. It was probably in a day or two. So we've probably got a factor of 100 to go if we're going to get as good at using stuff as nature is in converting sunlight into something useful. So how can we do that? Well, when we then come to look at what goes on in photosynthesis, one would have to say that it is a remarkably sophisticated engine that is replicated countless times in every green leaf. There are all sorts of bits here which I'm not going to talk about, but somewhere in here is the photosystem 2 complex, where photons are absorbed, channeled to the right place in the structure, where an electron and hole are separated. The key step, looking at it as a semiconductor physicist, is the solar cell bit. We split charges. The hole, the positive charge, is sort of the byproduct, and that's used to oxidize water to produce oxygen gas. And the electron is then, in a complicated way, it needs a further lift in photosystem 1, used to reduce the sort of engines of the chemistry that then produces carbohydrate, the NADPH in particular. But a huge number of steps and a very exquisite structure in there. And there are all sorts of other attributes there in photosynthesis which are astonishing. So one question is, how much stuff do you need to absorb sunlight? How thick do we need to make a layer of semiconductor or green plant? Well, the molecules, the conjugated molecules that we use in our light-emitting diodes or might use in solar cells are extremely good absorbers of light. So we need not much more than about 1/10 of a micron or 100 nanometers to get most light absorbed. It's really good. Silicon is a bad absorber of light, so we need a much, much more, about 100 times more, 10 microns. So silicon basically uses more. But nevertheless, 100 nanometers is, if you just stack dye molecules up, it's certainly several hundred. So there's a problem that we need, or nature needs quite a lot of molecules to do that job. And what it does is generate, again, very complex structures. And I'm picking up here images of so-called light harvesting complexes, which are antenna bundles of molecules that absorb light. Then the molecular excited states, or excitons, or whatever you want to call them, not yet free electrons and holes, are cascaded down to the reaction center where the charges are generated. And the reason, you might ask, why am I bothering to go here? Well, the answer is that the reason for that is that looking at this in some depth has generated some very surprising and quite profound mechanisms for the efficient energy transfer down to the reaction center. So this is a little image of a particular sort of protein block containing some colorful molecules. Oops. Right, I know what I did then. The Fenners-Matthews-Olsen complex. And what has been found is a beautiful work from the group of Graham Fleming in Berkeley, is that the way that energy might cascade around these molecules, you might regard as a bit like a traveling salesman problem. It would take a long time for energy to find the right way to get from where it was generated down to the reaction center. It's a figure of speech, and I should use it rather, well, I'm using it rather carelessly. Actually, these things run a little bit like quantum computers. They manage to set up quantum coherence over macroscopic distances. The excitation knows about all these 7 chromophores simultaneously, and it can explore all pathways and choose the most efficient one without having to do any trial or error. And it is an example of a coherent quantum phenomenon happening at room temperature. It's sort of at the side of that sort of broad, exciting space of quantum technology. But there it is working in green plants. And here it was put in green plants to deal with that matching of length scales, that we need sort of 200 or so molecules to get all the light that they absorb just down to one reaction center. Well, we have done lots of work, we being a large community of people working on nanomaterials, to try and ape what nature has done with molecules to get solar cells to work. We sort of cheat on how to get the structure set up to get light absorbed close enough to actually the junction where we can pull the charges apart. So there's a generic cartoon of 2 materials interdigitated, interconnected, so that we have enough surface between them that at the surface we can get charge generation. And it's kept a whole, well, several communities of nanomaterials people busy, and very interesting approaches to do that. You can certainly do with organics, and actually what is often done is just to mix up a material which will pull an electron away as an acceptor and leave a hole behind on the donor. There are lots of them which will do that, and we can get the right morphologies. And the great things with the organics is that we can mix everything up into some wonderful ink and print it. So there really are demonstrations of not necessarily good enough solar cells where there is additive manufacturing, roll-to-roll printing onto a plastic substrate, generating solar cells. Now, it doesn't exactly look like a leaf, but but there's not very much stuff in it, and it's that vision of being able to make functional objects with a very efficient use of material that is powerful and maybe compelling. So here's a couple of shots from our Cambridge effort in this space, 819. Here is a piece of roll-to-roll printed solar panel with a couple of cheerful and pleased people because it worked. And it's also done quite small scale. This is not a multi-billion pound fab. This is a roll-to-roll printer. So at this point, sort of back to are we being good for humanity? I will sort of briefly go again off message or away from Microsoft, at least I think away from Microsoft, to talk about something that we ended up doing when, having decided that we're going to try and make plastic solar cells, we discovered there wasn't a market for them. Because without subsidies in the developed world, large-scale solar doesn't really work. But there is a wonderful opportunity in the off-grid world where, particularly in Africa, but in other parts of the world too, providing light and also electrical charging for cell phones, because people may have no running water and no grid electricity, but they've certainly got cell phones, is really important. And if you can replace kerosene or paraffin, which is currently used for lighting in the off-grid world, with a solar panel, this happens to be one of our printed organic ones, but actually silicon does perfectly well, a box with a high-performance rechargeable battery, and the ones that Azura uses are lithium iron phosphate, very advanced lithium ion batteries, and then a gallium nitride LED light. All 3 pieces of technology which either didn't exist or were too expensive even a couple of decades ago, The composite is something which delivers high-quality lighting at less than half the real cost of burning kerosene. And kerosene, by the way, poisons people if it's burnt indoors. There's a problem about how to get it out into that community. The problem is that the upfront cost is high, and various pay-as-you-go mechanisms are, we think, are going to work, so that's the basis behind this Cambridge spin-off. But it is, I think it's an unalloyed good news story that technology actually can have a common good. But the off-grid world, of course, extends back to our world in the Internet of Things, where there's a very exciting opportunity, as we've sort of heard at various stages today, because all the sensing that is needed, all the IoT devices need to be powered up, and how they get powered up, how they scavenge energy from vibrations or light, how they store it, and then how they use that electrical energy very efficiently, it would appear to be a main driver for the widespread application of the sensors that the Internet of Things want and require. So the ability to integrate at low cost, not just the cost of the component, but the cost of manufacturing it into the sensor, is obviously very exciting for new ways of doing solar. There's a problem about how much area you need to get something which is useful. A business card in sunlight will produce about 1.5 milliwatts, and you can do quite a lot with 1.5 milliwatts. Indoors at around 200 lux, you're about half a milliwatt. So there's a challenge that we need. There's a real driver to be able to get solar to be more efficient. And if it can be more efficient, then it would find real benefit in remote sensing. So there are some little images of things of different sizes. So how do we make solar more efficient? So this is sort of back to science for the next few minutes. Well, I want to go back to a little bit more about how surprisingly undiscovered photosynthesis is. And that is that we have, I talked about one length scale, which has to be sort of engineered, or difference in length scales, and that was the amount of the thickness of material you need to absorb light to get, and then funnel it to the reaction center in photosynthesis. The other length scale is, it's a general problem for the organics, and that is that the electrostatics work against you. Electrons and holes, positive and negative charges, of course, pull together pretty strongly. In silicon, they're very strongly screened. There's a very high dielectric constant, so electrons and holes can sort of wander away from one another quite easily, which is why silicon cells work. But with the organics, and it doesn't matter whether it's our artificial systems or whether it's photosynthesis, that screening is much less effective. So we have to get electrons and holes about 10 nanometers apart. Otherwise, they would just, so we can pull them apart in this sort of charge generation stage. But if they don't get to that distance apart, they'll just come back together again, and we'll get heat, not electricity. Now, that's actually really good news, and we know that works because, that's why the organic LEDs work. Organic LEDs are really thin, and the reason we can get away with them being so thin is it's very easy to get the electrons and holes to come close enough that they pull together, and we get light from that process. So how on earth does the reverse process of charge separation work? So that initial generation step, we push an electron from a high energy state where it's been photoexcited up to, and it drops down to a lower energy level. And the problem is that the Coulomb potential, the electrostatics, would say, if nothing else happens, the electron appears to get stuck close to where it was generated, and we've got a barrier that has to be circumvented. So it's one of the things we've been looking at in my research group to try to understand how that can work. And we've been looking at the synthetic organic solar cell systems which work really well. So we've used empirical selection, which often doesn't get as much credit for scientific innovation or engineering innovation as it should do, but that's how it is. And what we discovered is that where we were looking at an electron and hole separating between the electron accepting bit, which is the circles here, and the hole accepting bit, which is the blue shaded area above, there was enough electric field between the electron and the hole to warp the color of actually the blue material a little bit. The electric field generated slightly redshifts the color of this thing, which we could then measure and calibrate and use as a voltmeter. And what we discovered is that for the systems which work well, the electron and the hole separate, and there isn't a length scale on here, by about certainly 5 nanometers within 10 to the minus 13 of a second. I forget how. I mean, I think that's. The electron hole traveling very, very quickly. They're traveling at about 10 to the 5 meters per second, but 10 to the minus 13 seconds is not a long time. But if they're going to travel that fast, then there has to be fully coherent motion. It's another example of a coherent, quantum coherent process. And it looks as though nature is doing that too in photosynthesis. There's some beautiful work from the Van Grandel group in Amsterdam on that. Some surprises. I don't think I need to show you that. So the final thing I want to do is muse a bit on what we might do with solar cells. And going back again to Peter Lee's talk this morning, where I think his assertion was anything you could dream of, and my rider is that doesn't disobey the second law of thermodynamics, because we don't go for perpetual motion machines, will be made and will work. So solar cells, and by the way, photosynthesis, are not very efficient. And the problem is that light comes in many colors. So here is the solar spectrum. The visible runs from 400 to about 700, and there's plenty of infrared in the solar spectrum. And the shaded red area is the part of the spectrum we could capture with a silicon solar cell, which is out to about 1.1 eV, about 1100 nanometers. So at a stroke, we had to make a choice as to where to draw the line, what part of the spectrum to throw away, and that's the longer wavelengths than the infrared. So we've done that. And then we start throwing more away. There's something we inevitably have to throw away due to sort of entropy factors that the Shockley-Queisser analysis showed some time ago. But there are other losses. So what we actually can use is the red shaded curve, and the stuff that's wasted is the difference between the grey and the red. And a lot of that wasted energy is that the lowest energy photon that's absorbed at 1.1 eV does just as good a job as a nice visible photon with an energy of 2.2 eV or higher. So by the time you get to 2.2 eV, there was enough energy to have created 2 electron-hole pairs, but in silicon we'll only get 1. So it's that limits the energy that you get from a single junction cell to about 33%. So the very best single junction cells based on gallium arsenide are up to, I think, 28.5%, but it's still not 100. What if nature had a bit more time to sort it out? Because it is the case that nature hasn't chosen to do that. Well, we can go a bit faster than nature, and there are elaborate but enormously expensive so-called tandem cells where we can tune different band gaps, different colors, taking the blue, the green, the red through successive cells and wire them all up in series. And those 3-5 semiconductor tandem cells can hit 40-45% efficiency now. They're expensive, they're wonderful for space satellites. They are not going to be deployed in solar farms. The sort of mad project we're working on at the moment is, could we do something with silicon itself? Could I take a silicon solar panel and put some magic coating on it, which would be a sort of buy one, get one free solar paint? This is stuff we haven't done yet, so it's probably unwise, but I just wanted to give a sense of where things may go. So if we could arrange that all those photons that have got enough energy to produce two electron-hole pairs could be captured by this top layer, and then we could split those photons into two excitations, and then the bit that is not yet demonstrated well is to transfer them both to the silicon. Then we would improve things quite a lot. For the UK contingent, it would be making, from a solar cell perspective, Marseille as sunny as Manchester as sunny as Marseille. So it's quite a big uplift. Now, it all has to do with electron spin, and I realize it's sort of late in the afternoon, but for those who know it, you will know that in an excited state, in a molecular excited state, I can pair electrons spin up, spin down to form a singlet state, and that's the one that emits light. But they can also go spin triplet, and spin triplets are what give phosphorescence. That's the luminous alarm clocks that don't contain radium are phosphorescence. And phosphorescence is a problem, and the problem is that these triplet states are lower in energy by quite a lot than the singlet excited states. And it's already a big deal for organic LEDs because as we bring electrons and holes together in an LED, 3 out of 4 collisions produce a triplet and only one produces a singlet. And that might have limited efficiencies to 25%, but I've already told you that efficiencies are at around 100% for OLEDs. And there have been some very clever ways around energizing the triplets so that they can become directly emissive. One of them is to allow triplets to collide with one another and they can fuse to form a singlet. There's enough energy to do that. But then there's a reverse process where if we can really make the triplet very low energy, when the triplet becomes half the energy of the singlet, they can split. The singlet can split to form a pair of triplets. It's a very interesting maximally quantum entangled pair of triplets that's overall spin 0. And the amazing thing is that that happens incredibly efficiently in some materials. It happens in 10 to the minus 12 of a second, so anything that happens that fast is going to be very efficient. So the scheme is we can use some of those materials that do that, and if, and there are plenty of ifs, where everything would work, then we can regain more efficiency in the visible part of the spectrum by getting twice the photocurrent from the visible. So that is the small thing that we're working on at the moment. And the various steps along the way, there's a wonderful, very excellent group in MIT who are trying to do the same thing. We had back-to-back articles in one of the Nature journals last autumn on the step towards making the triplet, which generally does nothing, useful by tunneling it into an inorganic nanocrystal, which works. So that's an aspiration, and if we haven't fried ourselves completely in 20 or 30 years' time, I'm sure solar will play a larger part in it. Along the way, it may have helped the Internet of Things along. That's the connection back to Microsoft. I hope I've left a few minutes for questions. Thank you.
Well, we do have some time for questions. I guess, as well as Internet of Things, we do run very power-hungry data centers. I don't know if you have any thoughts about that. And in the meantime, also, I'm curious, 8 and 19, are they atomic numbers? Or?
Oh, no, it takes 8 minutes, 19 seconds for light to travel from the sun to the Earth.
Oh, right.
Right, so
okay.
Now you will never forget the name of the company.
Shall we cover our data centers in
well, data centers. Yes, data centers are a big issue. I never know which number to believe, but the amount of energy, electrical energy we use in some way or other supporting data is rising rapidly. I think it's not quite as bad as air travel, is it? But it's sort of heading in that direction. I mean, the metric for the future is efficient generation, storage, and usage of electricity, isn't it? Across the piece. Solar may have a role in that.
Yeah.
Maybe we'll have our solar centers in sunny parts of Africa and the Middle East. Who knows?
I suppose they've got to work at night as well. So there's
there is that problem. Yes.
Any questions from the?
We need wonderful batteries. That came up this morning.
Of course, we may be approaching hunger time. Ken, here's the microphone coming.
I don't think I heard you say that nice roll-to-roll thin solar cell that you showed those two happy chaps holding.
Yes.
What's the efficiency of that at the moment?
The best organic solar cell efficiency is around 10% at the moment. The reason they're not higher is that there's a voltage loss for reasons that the open circuit voltage should be higher.
All right, so if it's 10%, if you coated that area of the US that you said in that
You would just have, yeah, I mean, it could be all right, yes. I was careful not to say that is tomorrow's technology. It was more the sort of vision that one can see ways of dropping costs and dropping the amount of material used. So I was stopping short of saying that's going to be tomorrow.
Other questions? There's one right over there, at the back. Bill.
So I have a question about displays, and it goes back to what we did as children, where we got two tin cans or two Dixie cups connected by a piece of string and made a walkie-talkie, and which proves that acoustic transducers are bidirectional. They can be. Can you speak to what the prospects are for effectively making displays where the pixels are likewise optical transducers are bidirectional, and therefore basically the LCD is also a CCD?
Oh, I couldn't hear quite as well, but bidirectional in the sense that it can be both a detector as well as an emitter.
Yes.
Yes. Absolutely. The easiest thing would be to put a fourth pixel in, which could be put in using essentially the same device architecture as used for the LEDs, and that fourth pixel would be a detector. Yeah.
Yeah.
That's certainly been talked about.
Yes, that we've actually done.
Yeah. Yeah. I think I knew that, yes.
Can we go past that?
Well, could we use the pixels? Could we not have to waste some real estate? It would be you've got to be careful. If you want something that absorbs all colors of light, you want to keep it away from where you're trying to emit light, because it would do some absorbing unless it were small. But it might be possible to park the detector behind the light emitter bit if you were very clever with the photonics.
Thank you.
It's a lot of engineering possibilities. I would say the photonics would probably come in rather importantly to be able to control where different colors do and don't see.
Any other questions out there? No. Butler in the back. Yes. Microphone coming?
No, it was just a comment.
Energy storage.
Yes.
Why can't I have organic batteries?
Well, I think you can. The problem with we're rather greedy about batteries, that we want them to have very high energy densities, and we want energy in a form, chemical energy in a form we can just run it down quickly. We haven't managed to make a battery. If we could use starch as the energy form for a battery, then that would be fine, but we don't know how to do that. Energy storage is such a complicated issue. I mean, one has to say that, and one would say that photosynthesis is often sort of given a bad name because its overall energy conversion efficiency of sunlight is down at below 1% for green matter on average. So the business of making carbohydrates is not completely efficient. Of course, nature's, green plants only have to outcompete other green plants. So it's not obvious that biomass is the smartest thing to do if you want to generate energy or a storable energy. But turning it into a battery is something I have no idea how to do. The question is a very good one.
Time for one last question, I think, over here.
I mean, there's a lot of talk of turning electricity into hydrogen and oxygen, which is fairly easy to do. I just have visions of sort of new generations of Hindenburgs. I mean, hydrogen is not actually that useful a form of stored energy. I mean, it won't solve the mobile device dilemma, I don't think.
One last question? Or maybe it's dinner time.
Dinner time.
Thank you for a fantastic talk.